close your eyes, if you like. There is nothing here that requires your attention, nothing that demands anything from you. Only a voice, and a story, and the quiet hours ahead in which to let it unfold at whatever pace suits you. Tonight, we are going to travel through time. Not quickly, there is no hurry here. We will move slowly and gently through the decades, pausing to look carefully at things that are worth understanding, letting the story breathe and settle as we go. By the time we reach the end, many hours will have passed, and the world outside will be exactly as you left it. But somewhere in the space between waking and sleep, you will have traveled further than you might expect. We are going to follow the story of the fighter jet. It is, at its heart, a story about human curiosity. About the particular kind of mind that looks at something that has always been done one way and asks, quietly but persistently, whether it might be done differently. Better. Faster. More precisely. With less weight, less drag, less visibility to the forces that would seek to stop it. The people in this story are engineers and pilots and designers and commanders, men and women who spent their working lives in the presence of extraordinary machines, pushing against the boundaries of what was physically possible, solving problems that had never been solved before because the problems themselves had never previously existed. They worked in wind tunnels and drawing offices and cockpits and hangars. They argued and collaborated and made mistakes and corrected them. They built things that did not work, understood why, and built them again differently. And gradually, across the span of 8 decades, they transformed aviation from something that had barely left its propeller-driven adolescence into one of the most sophisticated technological endeavors in human history. That transformation is what we are here to explore. The story begins in the 1940s, in the closing years of a world at war, when the first jet-powered aircraft appeared in the skies over Europe and changed, permanently and completely, the direction of aviation. It moves through the 1950s, when jets met each other in combat for the first time over the Korean Peninsula and rewrote the rules of aerial warfare at speeds the previous generation of pilots would have found almost unimaginable. It continues into the 1960s, when the sound barrier, once feared to be an absolute limit, became a routine threshold, crossed daily by aircraft that had been designed from the beginning to live on the other side of it. It passes through the difficult lessons of the 1970s, when combat in Southeast Asia revealed the gap between what technology had promised and what it could reliably deliver, and the aviation world responded with honesty and discipline, rebuilding its doctrine, its training, and its aircraft around what experience had actually shown. It moves into the era of agility and precision, when designers learned to build aircraft that could think ahead of their pilots and fly with a responsiveness that no previous generation of machine had achieved. It enters the quiet revolution of stealth, when the question changed from how fast to whether it could be seen at all, and aircraft began to pass through defended airspace like shadows. And it arrives in the present, and at the edge of the future, where jets have become networked platforms carrying artificial intelligence and directed energy and the seeds of a new kind of aerial warfare that is still taking shape. Each chapter tonight will take its time. That is intentional. This is not a place for rushing. The story has enough space within it for long, unhurried pauses, moments to sit with an idea, to let a detail sink in, to appreciate the quiet strangeness of what human beings have built when they set their minds to the problem of flight. If you drift, that is perfectly fine. The voice will be here when you return. The story will carry on at its own gentle pace, and wherever you find yourself within it, whether following every word or floating somewhere between waking and dreaming, you are exactly where you are supposed to be. The sky is vast and quiet tonight. Somewhere up there, beyond the clouds and the dark, the aircraft that this story is about are still flying, still crossing the threshold of sound, still invisible to the radars searching for them, still connected to networks that stretch from horizon to horizon. But that is their world. This, for now, is yours. Settle in. Get comfortable. Let everything else go quiet. The story is about to begin. By the way, if you find these videos helpful for relaxation or sleep, a like or subscription quietly supports the channel and helps more people discover it. Chapter 1. The first jet fighters. Near the end of the Second World War, a new kind of aircraft appeared in the skies over Europe. It did not rely on the spinning blur of propellers to pull itself through the air. Instead, it moved forward with a smooth and continuous force, a steady, invisible push from behind. To those who saw it for the first time, it must have seemed almost unnatural, almost silent compared to what had come before. A machine that simply moved. This was the jet fighter. And the world of aviation would never be the same. For more than 4 decades, the propeller had been the heart of powered flight. From the fragile biplanes of the First World War to the powerful, heavily armed fighters of the Second, every aircraft that had ever climbed into combat had done so by pulling itself forward, spinning blades cutting through the air, dragging the machine behind them. It was a system that worked. It had been refined over and over again, pushed to remarkable levels of performance. And yet, by the early 1940s, engineers and designers on multiple sides of the war had begun to sense a ceiling, a limit. The propeller, for all its elegance, could only do so much. The jet engine offered something different. Rather than pulling, it pushed. Hot gases expelled from the rear of the engine created a continuous forward thrust, a force that did not depend on rotating blades, did not wobble or shudder at high speed, and did not face the same fundamental aerodynamic limits that had begun to constrain propeller-driven aircraft. The first operational jet fighters emerged late in the war, developed separately and in parallel by engineers working in secrecy, under pressure, in countries that would soon find themselves standing on opposite sides of history. They were imperfect machines. They were experimental in almost every sense. But they flew. And in flying, they opened a door that could never be closed again. The earliest jet fighters were, in many ways, aircraft of transition. Their designers were working in genuinely new territory. There were no textbooks for this, no established traditions, no generations of accumulated wisdom to draw upon. And so, in certain respects, These early machines looked reassuringly familiar. Their wings, in particular, were straight, extending out from the fuselage in clean, uncomplicated lines, much like the propeller aircraft that had come before them. This was not an accident. Straight wings were well understood. Engineers knew how they behaved, knew how to build them, knew what to expect from them at the speeds aviation had reached up to that point. And in the early jet age, where so many other variables were uncertain, there was comfort in that familiarity. The wings were a known quantity in an equation full of unknowns. But straight wings carried a limitation. As speeds increased, as jet propulsion began pushing aircraft faster than anything that had flown before, the straight wing would begin to reveal its boundaries. That discovery, however, was still a few years away. For now, these early jets climbed into the sky on straight, careful wings, and that was enough. There was something else about these early machines that surprised the pilots who first flew them. At low speeds, during taxi, during takeoff roll, during the first moments of flight, a jet engine did not respond the way a piston engine did. Pull back on a throttle in a propeller aircraft and the engine answered almost immediately. The relationship between pilot and machine felt direct, physical, alive. A jet engine was different. It needed time. It needed to spool up, to build heat and pressure and flow before its full thrust was available. At low speeds, in those first critical moments, early jet fighters actually felt sluggish compared to their propeller-driven counterparts. A pilot climbing into the cockpit for the first time, accustomed to the immediate surge of a piston engine, might have found the sensation quietly unsettling. The machine seemed reluctant, slow to commit. But patience was rewarded. Because once that jet engine built to its full power, once the aircraft climbed to altitude and the speed began to rise, something remarkable happened. The gap between a jet and a piston aircraft did not merely close, it inverted entirely. At altitude, at high speed, the jet pulled away with an ease that bordered on the effortless. It simply kept accelerating where a propeller-driven aircraft would begin to struggle. The ceiling of what was possible seemed, suddenly, to have been lifted. Pilots who made the transition from piston aircraft to these early jets speak of a learning curve that was unlike anything else in their careers. It was not that the jet was more dangerous, exactly. It was that it required a fundamental rethinking of how a pilot interacted with the machine. The throttle response was different. The energy management was different. The instincts built over hundreds or thousands of hours of propeller flight did not transfer cleanly. Experienced pilots had to learn, for example, to think further ahead. Because the engine was slower to respond, decisions about power needed to be made earlier. A pilot who waited too long to advance the throttle might find themselves short of speed at exactly the wrong moment. The margin for certain kinds of error was narrower in ways that were not immediately obvious. And yet the margin in other ways, the sheer performance available once the aircraft was moving, was wider than anything that had come before. It was a trade. A profound and permanent trade. The demands of jet propulsion extended beyond the cockpit, too. They reached all the way down to the ground, to the runways these new aircraft needed in order to take off at all. A propeller-driven fighter, generating its thrust from the very first moment the engine turned, could begin accelerating meaningfully almost from a standing start. The airfields of the Second World War had been built with these aircraft in mind. Many were short, improvised, carved out of farmland or desert. They worked because the aircraft that used them were, by the standards of the jet age, relatively gentle in their takeoff requirements. A jet fighter in those early years needed more. The slower throttle response, the time required to build thrust, the higher speeds needed to generate sufficient lift from those straight wings, all of it meant that the ground roll before takeoff was substantially longer. Existing airfields, in many cases, were simply not adequate. Runways needed to be extended. New facilities needed to be planned and built. The infrastructure of aviation had to begin catching up with the machines it was meant to support. It was the first sign of something that would become a recurring theme in the jet age. New aircraft demanding not just new skills, but new everything. And then there was the matter of keeping these machines flying. The engineering that made jet propulsion possible was sophisticated in ways that introduced entirely new categories of maintenance challenge. Piston engines were complex, certainly. Any aircraft mechanic of the era would have attested to that freely. But their complexity was, by the 1940s, a well-mapped complexity. The problems that arose were familiar. The solutions were understood. Jet engines were not yet familiar. The temperatures involved were extreme. The precision required in certain components was extraordinary. The materials were sometimes experimental, sometimes in short supply, sometimes prone to failure in ways that took time and hard experience to understand. Ground crews who had spent years becoming expert in piston engine maintenance found themselves, in many ways, starting again. New training was needed. New tools were needed. New ways of thinking about what it meant to prepare an aircraft for flight were needed. Maintenance turnaround times, in those early days, were often longer than commanders would have wished. The availability of jet aircraft for operations was sometimes limited not by production, but by the sheer challenge of keeping them in airworthy condition. It was a growing pain, a friction that accompanied almost every genuinely new technology, and it would diminish with time. But in those first years, it was real. The fuel question was real too. Early jet engines were, by the standards that would eventually be achieved, remarkably hungry. They consumed fuel at rates that placed serious constraints on how far and how long these aircraft could operate. The range of early jet fighters was limited, notably more limited, in some cases, than the propeller aircraft they were beginning to replace. This was a significant tactical consideration. An aircraft that could outrun everything in the sky was of limited use if it could only do so for a short time before needing to return to base. Designers and engineers understood the problem clearly, and they were already working on it. Improvements in engine efficiency would come, gradually, then rapidly, as the technology matured. But in those first years, the jet fighter was a brilliant, powerful, and somewhat impractical machine. It was a promise as much as a weapon, a proof of concept written in metal and fire. And yet, despite the limitations, despite the shorter range and the longer runways and the steeper maintenance demands and the throttle responses that confounded experienced pilots, despite all of it, there was something undeniable about what these aircraft represented. They were faster. At altitude, in the conditions where combat increasingly took place, They were faster than anything that had come before them by a margin that mattered enormously. And speed, in aerial warfare, is not merely an advantage. It is often the advantage. The aircraft that can choose when to engage, when to disengage, when to press and when to withdraw, that aircraft holds a form of control over the battle that no amount of firepower or maneuverability can easily overcome. The pilots who flew these early jets understood that they were participating in something historic. Not simply a new kind of aircraft, but a new kind of flying. The propeller age, that long, remarkable chapter that had begun with the Wright brothers and stretched through 2 world wars, was drawing to a close. What was beginning in its place was something that none of them could fully see yet. Something that would reshape militaries, reshape borders, reshape the entire human relationship with speed and distance and the sky. These first jet fighters were imperfect. They were early. They were filled with compromise and limitation and the particular awkwardness of things that are genuinely new. But they flew. And in flying, they began something. The skies above the middle of the 20th century would never look quite the same again. Somewhere above the clouds, moving with a quiet and continuous force that owed nothing to propellers and everything to a new way of thinking about what was possible, the jet age had begun. It was only the beginning. Chapter 2: Korea and the First Jet Battles. The sky grew faster. It happened quickly, more quickly than almost anyone had anticipated. In the 5 years between the end of the Second World War and the outbreak of conflict on the Korean peninsula, jet technology had not merely been refined. It had accelerated. The aircraft that rose into combat over Korea in the early 1950s were meaningfully different from the cautious, experimental machines that had appeared at the tail end of the previous war. They were faster. They were more capable. And for the first time in history, they would meet each other in the air. The nature of air combat was about to change in ways that even the most experienced pilots could not entirely have predicted. The sky grew faster, and the men who flew through it had to grow faster with it. Before Korea, the question of what jet versus jet combat would actually look like had remained largely theoretical. The jets of the Second World War had appeared too late and in too few numbers to meet each other in meaningful engagements. Pilots and planners had ideas, had projections, had educated guesses drawn from wind tunnel data and performance calculations. But educated guesses are not the same as experience. Korea provided the experience. When opposing jet fighters met over the territory that pilots would come to call Mig Alley, that stretch of northwestern Korea where combat was most concentrated and most intense, the encounter was historic in the most literal sense. For the first time, jet-powered aircraft fought each other in sustained aerial combat. Everything that followed in the development of air warfare, every tactic and doctrine and design decision of the decades ahead, has some root in what was learned in that sky. It was, in a sense, the opening chapter of a new kind of warfare, one written at speeds the world had never seen before. One of the most visible differences between the jets of Korea and their predecessors was in the shape of the wing. Where the earliest jet fighters had carried straight wings, familiar, conservative, inherited from the propeller age, The aircraft over Korea swept their wings back at a pronounced angle, the leading edge angling rearward from the fuselage in a clean, decisive line. This was not merely aesthetic. It was physics. As aircraft approached higher speeds that were beginning to push toward the sound barrier, a straight wing created problems. The airflow over it began to behave in complicated, unpredictable ways. Drag increased sharply. Control became difficult. The swept wing was the engineering answer to this challenge. By angling the wing back, designers effectively reduced the component of airspeed acting directly against the wing's leading edge. The onset of those troublesome high-speed effects was delayed. The aircraft could fly faster, more smoothly, with more authority, than a straight-wing design of equivalent power would have allowed. It was one of those elegant solutions that, once understood, seems almost obvious in retrospect. But it had taken years of research, including the careful examination of captured wartime data, to translate the principle into reliable flying aircraft. Over Korea, swept wings were no longer experimental. They were standard. They were necessary. And they were fast. Fast is a relative word, of course. But the relativity here is striking. The air combat speeds routinely encountered over Korea were approaching nearly double what pilots had experienced in the propeller-driven battles of the previous decade. Engagements that had once unfolded at 300 miles per hour were now unfolding at 500, at 600, at speeds that compressed the time available to see, to decide, and to act. Think about what that means in practice. A pilot in the Second World War, spotting an enemy aircraft at a distance, might have had several seconds to assess the situation, adjust his position, and begin his attack or his evasion. At Korean War speeds, that same distance translated to a fraction of the time. The geometry of combat, the angles, the closures, the turning radii, all of it changed with speed. Maneuvers that had been reliable in the slower air of the propeller era became difficult or impossible. New geometries had to be understood, internalized, practiced until they became instinct. The sky was the same sky. The fundamental challenges of aerial combat, to see first, to position well, to act decisively, were the same challenges. But the pace at which all of it happened had been transformed. And transformation, in combat, demands adaptation. Among the most disorienting challenges facing jet pilots of this era was a phenomenon that had been observed and documented but was still, in practical terms, poorly understood by those experiencing it for the first time. It was called compressibility, and it occurred as aircraft approached the transonic region, that unsettled boundary where subsonic flight ends and the sound barrier begins. At those speeds, airflow over different parts of the aircraft reached different velocities simultaneously. In some areas, the air was already moving supersonically even while the aircraft as a whole had not yet crossed that threshold. The result was a turbulent, unpredictable mix, shockwaves forming and dissolving across the airframe, causing buffeting, causing control surfaces to lose their effectiveness, causing aircraft to behave in ways that had no precedent in any training manual. Pilots who encountered severe compressibility effects at altitude found themselves in machines that were not responding as expected. Controls that should have produced a roll produced something else, or nothing at all. Noses that should have pulled up instead pushed down. It was, by all accounts, deeply alarming. The aircraft momentarily becoming something almost foreign, a machine operating according to rules its pilot had never been taught. These experiences were not merely frightening. They were informative. Every encounter with compressibility, every report filed by a pilot who had brushed against that boundary and returned to describe it, added to a growing body of knowledge that engineers and designers used to improve their understanding. The transonic region was being mapped in real time by men in cockpits at considerable personal risk. The data they gathered, imprecise, subjective, sometimes harrowing, was invaluable. The tactics of aerial combat, meanwhile, were being rewritten almost continuously. The dogfighting techniques of the Second World War, the tight turning battles, the climbing reversals, the close-range guns work that rewarded a certain kind of instinctive three-dimensional thinking did not translate cleanly into the jet age. At higher speeds, turning circles grew larger. An aircraft that attempts to turn hard at high speed must accept either a much wider arc or a significant loss of energy. The intimate, swirling engagements of the propeller era were becoming more difficult to execute and more difficult to sustain. What replaced them was not immediately obvious. Pilots and tacticians worked through it operationally, in the air over Korea, adapting in real time to what was working and what was not. Speed and altitude became even more critical currencies than they had been before. Energy that, once lost, was expensive to regain. Engagements became somewhat more linear, somewhat more dependent on the initial geometry of the intercept. The pilot who arrived at the fight with an energy advantage, higher, faster, held an edge that was more decisive than ever. And yet the fundamentals persisted. Awareness, positioning, aggression at the right moment, and the ability to think clearly under extreme stress, these things remained what they had always been. The technology had changed. The human qualities that determined who came home had not. Through all of this evolution in speed and tactics and the shape of wings, one thing remained constant: the gun. It might seem surprising, in retrospect. These were the early years of what would become a revolution in aerial weaponry, a revolution that would eventually produce radar-guided missiles and beyond visual range combat and targeting systems of extraordinary sophistication. But in Korea, in the early 1950s, none of that had yet arrived in reliable, operationally practical form. When a pilot closed on an enemy aircraft and prepared to fire, what he reached for was a trigger connected to cannons or machine guns mounted in the airframe. As it had been in the First World War, as it had been in the Second, the gun demanded proximity. It demanded accuracy. It demanded a pilot place his aircraft in a position that was, almost by definition, also dangerous, close enough to an enemy to hit him, which meant close enough for the enemy to hit back. All of the high speed, all of the swept wings and jet thrust and technological advancement of the era, and at the end of it, the decisive moment still came down to a pilot, a gun sight, and the ancient, intimate geometry of close combat. That would change. But not yet. What was beginning to change, slowly, tentatively, in ways that pointed clearly toward the future, was the role of radar in combat aviation. Radar had existed during the Second World War, of course. Ground-based radar had been critical to the air defense of Britain. Airborne radar had been fitted to night fighters. But in the daylight, close-range combat of that war, Radar had been largely secondary to the human eye. You saw your enemy. You engaged. Over Korea, and in the broader defensive planning that surrounded that conflict, radar-assisted interception was beginning to emerge as a serious operational concept. Ground controllers with radar coverage could track incoming aircraft and vector defending fighters toward them with a precision that visual searching alone could never match. The fighter pilot was beginning to be integrated into a larger system, no longer simply an individual hunting in the sky, but a component of a coordinated network that could see further and react faster than any human eye. It was early. The integration was imperfect, the communication sometimes unreliable, the picture available to controllers incomplete. But the direction was clear. The future of air combat would not belong exclusively to the skilled individual. It would belong to the skilled individual embedded within an intelligent system. The age of the lone eagle was not over. It would never be entirely over, but it was beginning to share the sky with something larger. High altitude had always been a dimension of air combat, but over Korea it became more central than ever before. The performance characteristics of jet engines, their efficiency and power at altitude, the thin air that allowed aircraft to reach higher speeds with less drag, made the upper atmosphere an increasingly important arena. Pilots regularly engaged at altitudes that would have been extreme by the standards of the previous war. High altitude brought its own demands. The cold was severe. The air was thin enough that a loss of cockpit pressurization could incapacitate a pilot within seconds. Navigation and situational awareness became more challenging when the ground was a distant abstraction far below. And the margin for error, always narrow in combat, became narrower still in an environment where the aircraft was operating near the edges of its performance envelope. Training expanded to address these realities. The transition programs that prepared pilots for jet aircraft during and after the Korean period were substantially more comprehensive than anything that had existed in the early jet years. There was more to learn, more systems, more aerodynamic knowledge, more procedural complexity. The pilot of a Korean War-era jet fighter needed to understand things that his propeller-era counterpart had never been required to consider. He needed to know what compressibility felt like, and what to do about it. He needed to understand the energy management demands of swept-wing flight. He needed to be comfortable in a cockpit that was pressurized and temperature-controlled and filled with instruments that would have seemed extraordinary a decade earlier. The bar had risen. It would keep rising. By the time the guns fell silent on the Korean peninsula, something had been settled that had still, in some ways, been an open question when the war began. The jet age was not an experiment. It was not a temporary divergence from an aviation world that would eventually return to propellers and familiar ways of flying. What had begun in those last years of the Second World War, with straight-winged aircraft whose engines struggled to respond and whose runways stretched longer than commanders wished, that beginning had matured into something decisive and permanent. Swept wings cut through the high-speed air with authority. Jet engines powered aircraft to altitudes and velocities that left the propeller era definitively behind. Pilots had learned, through hard experience in a hard sky, how to fight at speeds that would have seemed almost fantastical to their predecessors. The tactics were new. The training was new. The very shape of the aircraft overhead was new. The jet age was not coming. It had arrived. And the sky, that vast, indifferent, beautiful expanse through which human beings had been learning for half a century to move, had changed its character entirely. Faster, higher, further, and it was only getting started. Chapter 3: Supersonic Flight. For the first time, aircraft pushed beyond the speed of sound. It had not been easy. The sound barrier, that invisible boundary in the air where pressure waves pile up ahead of an accelerating aircraft and resist its passage with a force that engineers had once feared might be absolute, had demanded years of research, years of incremental progress, years of test pilots climbing into experimental aircraft and pushing further than anyone had gone before. There had been buffeting and lost control and, in some cases, lost aircraft. The barrier had felt, for a time, like exactly what its name implied, a wall, a limit. Something the physical world had placed in the path of human ambition and intended to hold firm. And then, quietly, it gave way. By the time the 1960s arrived, what had once been an experimental achievement, a single aircraft, on a single carefully prepared flight, briefly touching the speed of sound and returning with data that startled the world, had become routine. Military aircraft were crossing that threshold regularly, operationally, as a matter of course. The sound barrier had not disappeared. It had simply been demoted, from a wall into a door. And the door was open. What lay beyond it would reshape the design of aircraft, the training of pilots, and the nature of aerial combat in ways that are still felt today. The engine that made supersonic flight routine was, in its basic form, the same jet engine that had powered the aircraft of the Korean War. But it had been given something new. Something that pilots would come to think of almost as a reserve, a resource held back for moments of need, a burst of additional capability that could be called upon when ordinary performance was not enough. It was called the afterburner. The principle was straightforward, even if the engineering was not. A conventional jet engine, burning fuel in its combustion chamber and expelling hot gases rearward, does not consume all of the oxygen present in the airflow passing through it. There is oxygen remaining in the exhaust. The afterburner, a section added to the rear of the engine, behind the turbine, injects additional fuel directly into that exhaust stream and ignites it. The result is a secondary combustion, a second burst of heat and energy that substantially increases the thrust available to the aircraft. The increase is significant. An afterburner can add 50% or more to an engine's thrust output. That additional power is what allows an aircraft to cross the sound barrier, to accelerate through the transonic region where drag peaks sharply, and to sustain supersonic flight in conditions where a conventional engine alone would fall short. The cost is fuel. Afterburners are extraordinarily hungry. An aircraft burning in afterburner consumes fuel at a rate that makes the already limited range of early jet fighters seem generous by comparison. Pilots learn to use afterburner precisely for takeoff in certain conditions, for the push through the transonic region, for the specific moments in combat or intercept where speed was most critical. It was not a setting to be left engaged. It was a resource to be spent wisely. But when it was needed, it was there. And what it enabled, routine, operational supersonic flight, changed everything. Speed, at the extreme end of the performance envelope, is ruthlessly demanding of shape. An aircraft designed to cruise comfortably in the subsonic world, round-edged, relatively thick-winged, shaped to generate lift efficiently at moderate speeds, encounters the supersonic regime with all of those comfortable shapes working against it. Every curve, every blunt leading edge, every surface that is generous with lift at low speed becomes a source of drag at high speed. The air at those velocities does not flow gently around obstacles. It compresses and resists and extracts a price for every imperfection in the aerodynamic form. The answer, developed through intensive research and wind tunnel testing, was to make the aircraft thin. Dramatically, almost severely thin. Wings that in cross-section were barely more than flat plates, with leading edges sharp enough to cut. Fuselages that tapered and narrowed with a precision that had not been necessary in the more forgiving subsonic world. Every surface carefully considered, carefully shaped, with the goal of presenting the minimum possible profile to the air rushing past at supersonic velocities. These thin, swept wings were a departure even from the Korean War designs that had seemed so advanced just a decade earlier. They looked different. They felt different in flight, less forgiving at low speed, requiring higher approach and landing speeds, demanding more precision and more attention from the pilot during the phases of flight that were, in some ways, most unforgiving. But at high altitude, in the supersonic regime for which they had been designed, they were in their element. Efficient, clean, capable of sustaining speeds that would have seemed extraordinary just years before. The shape of the aircraft had been transformed by the demands of the speed it was being asked to achieve. And the speed, in turn, was transforming everything else. The fighter aircraft of the 1950s had been, in their conception, balanced machines, designed to dogfight as well as to intercept, to turn and climb and engage in the kind of close, swirling combat that had characterized aerial warfare since the First World War. The supersonic interceptors of the 1960s represented, in some cases, a deliberate departure from that balance. If the primary threat was a bomber, large, powerful, capable of carrying weapons of catastrophic destructive potential, approaching at high altitude and needing to be stopped before it reached its target, then the aircraft best suited to stop it was not necessarily the most maneuverable aircraft ever built. It was the fastest. An interceptor that could climb rapidly, accelerate to supersonic speed, close on the incoming threat, and deliver a weapon solution before the bomber reached its release point was worth more, in that specific scenario, than an aircraft with a tighter turning circle. This logic drove a generation of aircraft design towards speed and climb rate, sometimes at the explicit expense of the close-range maneuvering performance that traditional fighter pilots valued most. Some interceptors of this era were genuinely limited in their ability to engage in the kind of combat their predecessors had been trained for. They were optimized for a specific threat, a specific geometry of interception, and within that geometry, they were formidable. The debate this created, between the advocates of pure speed and the advocates of balanced performance, would not be resolved in the 1960s. It would continue, intensify, and produce some of the most consequential arguments in the history of military aviation. But the interceptors were not arriving at their targets with guns alone. The weapons mix was changing, and changing significantly. Missile systems had been developing alongside the aircraft themselves. The guided missile, a weapon that could be launched at a target from a distance and directed by radar or infrared sensing to its destination without requiring the launching aircraft to close to gun range, offered a theoretical revolution in aerial combat. If the missile worked as intended, the pilot need never enter the close-range envelope where he was vulnerable. He could engage from miles away, at speeds and altitudes where traditional gunnery was impossible, and rely on the missile's own guidance to complete the attack. By the 1960s, missiles were no longer theoretical. They were standard equipment on frontline fighter aircraft. The gun, that constant of aerial warfare from its very beginnings, began in some cases to be removed entirely. A weight-saving, a space-saving, a statement of confidence in the new weapons and the doctrine that accompanied them. Some aircraft left the factory with no gun at all, armed entirely with missiles, designed for a style of combat in which the close-range engagement was assumed to be obsolete. That assumption, as the decade progressed and combat experience accumulated, would prove to be premature. But it was sincerely held, and it was not unreasonable given what was known at the time. The missile age had arrived, even if its full implications were still being worked out. To find a target at supersonic speeds, to detect it at a range that allowed a useful intercept, to track it with sufficient accuracy to guide a missile, required sensors that the human eye could not provide. The radar systems fitted to combat aircraft improved substantially through this period, extending their detection range and their reliability, becoming more capable of sorting real targets from the background noise that had plagued earlier designs. An aircraft with a capable radar could find its target in darkness, in cloud, at ranges where visual acquisition was simply not possible. The pilot was no longer entirely dependent on his own eyes and the eyes of ground controllers. He carried, in his aircraft, a system that could reach out through the sky and find what he was looking for. This integration of radar into the fighter aircraft itself, not as an accessory, but as a central and defining capability, changed the nature of the pilot's role in ways that were profound. He was becoming, increasingly, an operator of a system as much as a flyer of an aircraft. The skills of situational awareness, of interpreting what the instruments were telling him, of managing multiple information streams simultaneously, were becoming as important as the physical skill of handling the aircraft itself. Both remained essential. But the balance had shifted. The cockpit that surrounded the pilot of a supersonic aircraft in the 1960s was a different environment from anything that had come before. Instruments multiplied. Switches multiplied. The systems that needed to be monitored, managed, and operated in flight, the radar, the weapons, the engine management, the navigation, the communication, all of it had grown more complex, more capable, and more demanding. A pilot climbing into the cockpit of a high-performance aircraft of this era faced a wall of information. Dials and gauges covered panels that would have seemed impossibly crowded to a pilot from the previous decade. Procedures that needed to be followed precisely, in the right sequence, under the pressure of flight, required a depth of systems knowledge that training programs had to work hard to instill. The cockpit had always been a demanding environment. Aviation had always required pilots to manage multiple tasks simultaneously while also flying the aircraft with precision. But the complexity of the supersonic era represented a step change, a new level of cognitive demand that influenced how pilots were selected, how they were trained, and how long it took before a newly qualified aviator was considered ready for operational duties. And then there was the body itself. At extreme altitudes, the heights that supersonic interceptors regularly reached, the human body required protection that went beyond a warm jacket and an oxygen mask. The pressure of the atmosphere at those altitudes was too low to sustain consciousness, let alone performance. The temperature was severe. A sudden loss of cockpit pressurization at high altitude was not merely uncomfortable. It was potentially fatal within seconds. Some aircraft, and some operational profiles, required pilots to wear full pressure suits, garments that surrounded the body and maintained a survivable pressure environment even if the cockpit environment failed. These suits were elaborate, uncomfortable, and restrictive. They made the physical task of flying more demanding. Moving the head, reaching controls, maintaining the spatial awareness that combat demanded, all of it was harder in a pressure suit than in ordinary flight clothing. But they were necessary. And wearing them, sealed against the extreme environment of the upper atmosphere, pilots of the supersonic era operated in conditions that set them apart from every generation of aviator that had preceded them. They were flying at the edge of the atmosphere. They were, in a meaningful sense, touching space. All of this speed, the afterburners, the thin wings, the missiles, the radar, the pressure suits, the complex cockpits, had a consequence that reshaped the fundamental geometry of aerial combat. Time compressed. An aircraft approaching at supersonic speed covers ground at a rate that leaves almost no room for deliberation. The detection range at which a defensive system needed to identify and react to an incoming threat expanded dramatically, because the time available between detection and impact had shrunk just as dramatically. Decisions that might once have been made over minutes were now being made over seconds. The entire cycle of detect, identify, engage, and assess had to be faster. Faster in the systems, faster in the communication, faster in the human mind at the center of it all. The engagement timelines of supersonic combat were not a refinement of what had come before. They were a transformation. The air war of the 1960s bore a family resemblance to the air war of the 1940s in the same way that a modern city bears a family resemblance to the village from which it grew. The underlying purpose was recognizable. The scale and pace were entirely different. Speed had become, in the design philosophy of this decade, the primary goal. Not the only goal. Altitude capability, radar range, weapons load, and reliability all mattered enormously. But speed sat at the top. Speed was what the threat demanded, speed was what the doctrine required, and speed was what the technology of the era made possible in ways that had not existed before. The aircraft that filled the skies of the 1960s, lean, swept, supersonic, carrying missiles and radar and pilots in pressure suits, were machines that would have been unrecognizable to the engineers who had built the first operational jets just 20 years earlier. 20 years. In the span of a single career, aviation had traveled from propeller-driven aircraft straining against the limits of 300 miles per hour to sleek, supersonic interceptors pushing past twice the speed of sound. The sound barrier had given way. The sky had opened. And the aircraft that flew through that open door were, in every meaningful sense, a different kind of machine, born of a different era, shaped by different physics, demanding different skills, and carrying the world into a future that was moving, like everything else in this story, very fast indeed. Chapter 4: Vietnam and Lessons Learned. Technology promised distance. It was a reasonable promise, and it had been made in good faith. The missiles, the radar, the supersonic interceptors optimized for speed over turning performance, all of it had been built on a coherent vision of what modern aerial combat would look like. The enemy would be detected at range. A missile would be launched. The threat would be eliminated before it ever came close enough to be seen with the naked eye. The close, swirling, dangerous intimacy of old-fashioned dogfighting would be a thing of the past, a relic of a slower, simpler era that the technology of the 1960s had permanently left behind. And then the war in Vietnam began in earnest. And reality, as it has a habit of doing, arrived with its own set of opinions. The sky over Southeast Asia did not resemble the sky that doctrine had imagined. The engagements did not unfold at the ranges the missiles had been designed for. The threat was not a high-altitude bomber on a predictable course, following a geometry that radar-guided interceptors had been optimized to address. The threat was fast, maneuvering, often at close range, in an environment cluttered with geography and cloud and the chaos that real combat produces in abundance. Aircraft found themselves closer together than doctrine had intended. And pilots, finding themselves there, adapted. The missiles had seemed so promising. In testing, against cooperative targets, in conditions designed to demonstrate their capabilities, they had performed with an authority that justified confidence. The numbers, range, probability of kill, the geometry of the engagement envelopes, all pointed toward a weapon system that made close-range combat unnecessary. Why accept the risks of getting close when you could destroy a target from miles away? The answer that Vietnam provided was uncomfortable and unambiguous, because the missiles did not always work. Early air-to-air missile reliability, under the conditions of actual combat rather than controlled testing, proved to be significantly lower than anyone had planned for. Missiles failed to track. They failed to guide. They detonated prematurely, or failed to detonate at all. They were sensitive to the electronic environment, to the thermal background, to the specific geometry of the engagement in ways that had not been fully understood before pilots began firing them in earnest. The gap between what the weapons were supposed to do and what they actually did in the confusion of real aerial combat was wide enough to be alarming. Some engagements saw multiple missiles fired without a single kill. Pilots who had relied on the promise of standoff engagement found themselves, missiles expended and the enemy aircraft still flying, with nothing left to offer the fight. Nothing, that is, except the close-range maneuvering skills that doctrine had told them they would not need. It was an expensive lesson, but it was learned. The aircraft had been built for the wrong war. Some of them, several prominent American fighters of the era included, had left the factory without guns, their designers and their procurement systems confident that the missile age had made close-range weaponry obsolete. That confidence now revealed itself as a vulnerability. When combat closed to the ranges where missiles were ineffective or could not be used, when two aircraft were maneuvering hard in each other's immediate vicinity, when the geometry of the fight had collapsed to the kind of intimate distances that the last generation of gun-armed pilots would have recognized instantly, a fighter without a gun was a fighter without options. The pilot could maneuver. He could attempt to disengage. He could do everything right and still find himself unable to convert a position of advantage into a kill, because the weapon the situation demanded was not there. The gun came back. It did not come back quietly or tentatively. It came back with the force of operational experience behind it. The testimony of pilots who had been in those engagements, who knew what they had needed and had not had it. Modifications were made to aircraft already in service. Some carried gun pods externally, a solution that was aerodynamically imperfect but operationally necessary. Future designs were drawn with internal guns built in from the beginning. The pendulum, which had swung so decisively toward the missile in the previous decade, swung back, not to abandon the missile, which remained an essential weapon, but to restore the balance that operational experience had shown was necessary. The lesson was not that missiles were wrong. They were not wrong. They were the future. But they were not the only future. The close-range fight had not been made obsolete. It had merely been neglected. If the gun was coming back into the cockpit, then the skills to use it had to come back into the training program. Visual combat, the close-range, high-energy maneuvering engagement where a pilot had to see his opponent, track his movement, anticipate his intentions, and place his own aircraft in the precise position required to deliver fire, had to be relearned, re-emphasized, rebuilt into the foundation of what it meant to be a fighter pilot. This realization produced, over the course of the Vietnam period and in its immediate aftermath, some of the most significant reforms in military pilot training that the jet age had seen. Programs were developed specifically to restore and develop the close-range combat skills that doctrine had allowed to atrophy. Pilots flew against other pilots in dedicated air combat training, building the instincts and the physical understanding of three-dimensional maneuvering that could not be taught in a classroom. The philosophy behind these programs was simple and hard-won. You could not simulate your way to competence in aerial combat. You had to do it. You had to put pilots in aircraft and have them fight each other, within safe constraints, and let the feedback of that experience build the skills that no amount of academic instruction could replicate. The improvement in combat performance that followed the implementation of these training reforms was measurable and significant. Experience, even simulated experience, was irreplaceable. The aircraft that fought over Vietnam were not only fighting other aircraft. A significant and demanding portion of the air war was conducted against targets on the ground, supply lines, infrastructure, military installations, concentrations of equipment and personnel. The air-to-ground mission was not new, but its scale and complexity in this conflict drove a shift in how military aviation thought about the purpose of a combat aircraft. The interceptor of the early supersonic era had been conceived for a single primary mission. It was optimized for that mission, designed around its specific requirements, and accepted whatever limitations came with that optimization. The multi-role aircraft, a design philosophy that sought to build a single airframe capable of performing effectively across the full range of combat missions, from air to air to air to ground, began to emerge as a more attractive and more practical alternative. The logic was partly economic. A single aircraft type that could do multiple jobs was cheaper to procure, cheaper to maintain, and simpler to support logistically than a stable of specialized machines, each requiring their own training pipelines, their own spare parts, their own procedures. But it was also operational. A conflict like Vietnam, with its shifting demands and its wide variety of mission types, rewarded flexibility. An aircraft that could be tasked for close air support in the morning and an air superiority mission in the afternoon was worth more, in that environment, than a specialized machine that could only ever be one thing. The multi-role concept was not without its compromises. A design optimized for everything is, inevitably, optimized for nothing in particular. The balancing act between competing requirements, the weight, the aerodynamic characteristics, the systems, was genuinely difficult. But the operational logic was compelling, and it would shape aircraft development for decades. Not all survival in the skies over Vietnam depended on flying faster or maneuvering harder. Some of it depended on not being seen, or more precisely, on not being found by the electronic systems that were increasingly used to detect, track, and target aircraft. Surface-to-air missiles posed a serious threat to aircraft operating over defended territory. Radar-guided, capable of engaging targets at altitudes that had once seemed safe from ground fire, they demanded a response that was not simply about flying higher or faster. The response was electronic, systems designed to detect radar emissions, to warn pilots that they were being tracked, to confuse or deceive the guidance systems that were trying to find them. Electronic countermeasures improved substantially through this period, driven by the urgent operational need that combat provided. Aircraft were fitted with warning receivers that told pilots when radar was painting them. Jamming systems attempted to degrade the quality of the radar picture available to the threat. Tactics evolved to exploit the limitations of the surface-to-air missile systems, the angles from which they were most vulnerable, the maneuvers that made guidance more difficult, the altitudes and speeds that reduced their effectiveness. It was a continuous contest, a back and forth between the electronic capabilities of the offense and the defense, each side adapting to what the other had deployed. It had been called, and would continue to be called, an electronic war. And it was one that never truly ended, because the technology on both sides never truly stopped developing. The pilot who emerged from Vietnam was asked to be something that no previous generation had quite been asked to be. He had to be a dogfighter, rediscovering the close-range combat skills that the missile age had threatened to make obsolete. He had to be a systems operator, managing radar and weapons and electronic equipment that demanded understanding and attention. He had to be an air-to-ground specialist, capable of delivering weapons accurately against defended targets at low altitude. And he had to manage the balance between speed and agility, understanding when to push for energy, when to trade it, when the fight demanded acceleration and when it demanded turning. Speed and agility are, to a degree, competing qualities. An aircraft optimized for pure speed tends to have the thin, swept surfaces that are less efficient at generating lift for turning. An aircraft with the broad, powerful wings that enable tight maneuvering carries drag that limits its top speed. The design tension between them was real, and it played out in every drawing office and requirements document of the era. What Vietnam argued, through its operational evidence, was that the answer was not to choose one at the expense of the other. The answer was to find the balance, to build aircraft that could accelerate to energy advantage and then use that energy in a maneuvering fight, that could go fast when fast was what the situation required and turn hard when turning was what survival demanded. Balance, not specialization. Versatility, not purity. It was easier to state as a requirement than to achieve as engineering. But the requirement was clear. Out of this experience, the uncomfortable surprises of missile performance, the return of close-range combat, the expansion of missions, the growth of electronic warfare, the re-emphasis of pilot training, something valuable was being built. It was not visible in any single aircraft or any single decision. It was an accumulation. A body of knowledge, hard-won and paid for in full, about what aerial combat actually looked like when it was stripped of assumptions and confronted on its own terms. That knowledge found its way into requirements documents and design briefs. It found its way into training curricula and tactical manuals. It found its way, eventually, into the next generation of aircraft. Designs that would be shaped, at their foundations, by what the skies over Southeast Asia had taught. The fighters that would emerge in the years ahead, more balanced, more capable, more honestly conceived against the reality of combat rather than the theory of it, owed a significant debt to a war that had been, in so many ways, a painful education. The aircraft that would come to define the next era of aerial combat were built, in part, from lessons written in a sky that had refused to cooperate with the assumptions that had been brought to it. Technology had promised distance. Vietnam had answered with proximity. And aviation, as it had always done when confronted with the gap between what was planned and what was real, adapted. The pilots came home with knowledge that no wind tunnel could have provided. The engineers listened, and the designers drew new lines, and the next generation of aircraft began to take shape with the shadows of those Southeast Asian skies somewhere in their bones. The air was changing again. It always was. Chapter 5. Air superiority and agility. Speed was no longer enough. The lessons had been absorbed. The reports had been written, the after-action analyses completed, the uncomfortable truths acknowledged and built into the foundations of what came next. Vietnam had made the argument clearly and at considerable cost. An aircraft that could only go fast was an aircraft with a gap in its capability, a gap that real combat would find and exploit. Speed mattered. It had always mattered, and it always would. But speed alone, without the ability to control that speed, to direct it, to translate it into precise and responsive movement at the moment the fight demanded, was incomplete. What the next generation of aircraft needed was something more nuanced. Something that the designers of the pure interceptors had, in their focus on the supersonic regime, allowed to recede. Control. Precision. The ability to move, to turn and climb and reverse and accelerate, with a responsiveness that matched the demands of the close-range fight that combat had proven was never going away. Air aircraft began to feel more responsive than ever before. And the story of how that happened is, in many ways, the story of how modern aviation was made. The shift began in the design offices. In the years following Vietnam, as the lessons of that conflict worked their way through the military aviation establishments of the major powers, a new set of priorities began to take shape in the requirements that engineers were asked to meet. Maneuverability. The word appeared in briefings and documents with a new emphasis, not as one quality among many to be balanced against speed and range and payload, but as a primary goal, a defining characteristic of what the next generation of fighters needed to be. An aircraft that could outmaneuver its opponent in a close-range engagement held an advantage that no amount of speed alone could reliably overcome. The pilot who could point his aircraft where he needed it, when he needed it, with precision and authority, was the pilot who controlled the geometry of the fight. Designers returned to first principles. They examined what maneuverability actually required, what physical and aerodynamic qualities determined how quickly and how tightly an aircraft could change its direction, how much energy it lost in doing so, and how quickly it could recover that energy for the next demand the fight placed upon it. The answers informed everything from wing shape to engine selection to the distribution of weight within the airframe. Maneuverability was not a single quality. It was a constellation of qualities, all of which had to be designed in from the beginning, because they could not meaningfully be added later. At the heart of the new maneuverability was thrust. Specifically, the relationship between the thrust an engine could produce and the weight of the aircraft it was moving. The thrust-to-weight ratio, a number that told you, more directly than almost any other single figure, how a fighter would feel to the pilot who flew it. An aircraft with a thrust-to-weight ratio below 1, meaning the engine produces less thrust than the aircraft weighs, is always working against gravity in a climb. It can climb, given sufficient speed and lift, but the engine alone cannot pull it vertically upward. An aircraft with a ratio at or above 1 is different in kind. Point it straight up, and it will accelerate. It does not merely sustain a climb, it rushes into one, trading engine power directly for altitude with an authority that changes the entire character of what the aircraft can do in a fight. The fighters designed in the wake of Vietnam pushed their thrust-to-weight ratios toward, and in some cases beyond, that threshold. The engines of the era were producing more thrust from smaller, lighter packages than had previously been possible, and aircraft designers made the most of it. The result was fighters that climbed with urgency, that could recover lost energy quickly, that could sustain maneuvering demands without bleeding down to the sluggish, vulnerable speeds at which an aircraft becomes easy prey. High thrust-to-weight was not a magic solution. An aircraft that could accelerate vertically was still subject to all the other demands of the fight: positioning, awareness, the quality of the pilot's decisions. But it changed what was possible. It expanded the vocabulary of maneuver available to the pilot, adding words to the language of aerial combat that had not existed before. But thrust and aerodynamic shape, for all their importance, could only take the responsiveness of an aircraft so far. There was a limit to what mechanical flight controls, cables and pushrods and hydraulic actuators, physically connecting the pilot's inputs to the control surfaces, could deliver in terms of precision and immediacy. The systems worked. They had worked reliably for decades. But they carried inherent limitations, a degree of lag, a resistance to rapid or extreme inputs, a physical complexity that added weight and required careful maintenance. The answer that engineers developed, an answer that would prove to be one of the most consequential technologies in the history of aviation, was to remove the direct mechanical connection between the pilot and the control surfaces entirely. Fly-by-wire. Instead of cables and rods, electrical signals. The pilot's inputs, the movement of the stick, the pressure on the rudder pedals, were converted into electronic signals that were processed by computers before being sent to the actuators that moved the control surfaces. The mechanical middleman was gone. In its place was software, code running on computers that could interpret the pilot's intentions, process information about the aircraft's current state, and send precisely the right commands to the right surfaces at the right moment. The immediacy this enabled was remarkable. Electrical signals travel faster than mechanical linkages can move. Computers can process multiple inputs simultaneously and respond in fractions of a second. The control surfaces of a fly-by-wire aircraft responded to pilot inputs with a precision and speed that the mechanical systems they replaced could not match. The aircraft felt, to the pilot, more direct, more connected, more like an extension of his own intentions and less like a machine he was operating from a distance. Fly-by-wire enabled something else, something that would have been simply impossible with conventional mechanical controls. It enabled designers to build aircraft that were deliberately, intentionally unstable. This requires a moment of explanation, because instability in an aircraft sounds, at first consideration, like exactly what you do not want. The long tradition of aircraft design had been oriented toward stability, toward producing aircraft that, left to their own devices, tended to return to level flight, that did not demand constant correction from the pilot, that were forgiving of momentary inattention. Stable aircraft are predictable. They are, in many ways, easier to fly. But they have a quality that is, in a maneuvering combat context, a limitation. They resist change. An aircraft that naturally wants to fly straight and level must be persuaded, with some force and some lag, to deviate from that preference. Every maneuver is, at some level, a fight against the aircraft's own inclination to remain where it is. An unstable aircraft is different. An aircraft balanced on the edge of instability, or beyond it, in a region where it would diverge and depart from controlled flight without constant correction, wants to move. It is, in a sense, always ready to maneuver. The resistance is gone. The inputs required to change direction are smaller, the response is faster, the aircraft more immediately obedient to the pilot's intentions. The reason such aircraft had never been built before was simple. A human pilot cannot provide the constant, rapid, precise corrections required to keep an unstable aircraft under control. The task is too fast, too demanding, too unforgiving of the slight lags and imprecisions that are inherent in human reaction time. But a computer can. And that was precisely what fly-by-wire computers were now doing, running continuously, monitoring the aircraft's state hundreds of times per second, making the tiny corrective inputs that kept the aircraft on the edge of control, translating the pilot's commands into the precise combinations of surface movements required to execute them. The pilot asked for a maneuver. The computer made it happen, managing the instability invisibly, presenting the pilot with an aircraft that responded to his intentions with a directness that felt almost effortless. The aircraft was more maneuverable than anything that had come before it. And the pilot, paradoxically, had less work to do to make it move. In close-range combat, the aircraft that emerged from this philosophy were formidable in ways that the pure-speed interceptors of the previous era had not been. The dogfighting capability of the new generation of fighters was not an accidental byproduct of their design. It was the explicit goal that had driven the design from the beginning. The ability to point quickly, to bring the nose of the aircraft around to bear on a target with speed and precision, had become a critical metric. Energy management, the art of maintaining the speed and altitude that gave options in a fight, was built into the aerodynamic character of the aircraft. Control at high angles of attack, the steep, nose-high attitudes that could occur in the most aggressive phases of maneuvering combat, was improved, allowing pilots to sustain effective control in regions of the flight envelope where earlier aircraft had become unresponsive or dangerous. The sum of these qualities was aircraft that a skilled pilot could use with a confidence that the previous generation's designs had not always inspired. The machine was, in the fullest sense, a partner in the fight, responsive, capable, honest in its behavior, rather than a powerful but sometimes frightening tool that had to be managed carefully even as it was being asked to perform. The new generation of fighters was not a single family of aircraft. It was, perhaps most notably, two families, complementary in concept, different in emphasis, representing a deliberate division of the air superiority mission into its component parts. On one side were the lightweight fighters. Smaller, simpler, less expensive, optimized relentlessly for the close-range maneuvering fight. Every design decision evaluated against the question of whether it improved the aircraft's agility or burdened it unnecessarily. These were aircraft that a pilot could feel completely, that responded to inputs with an immediacy that made them feel like extensions of the body rather than machines. They were not long-range aircraft. They were not heavy weapon carriers. They were, purely and completely, fighters, and in that role, they were exceptional. On the other side were the larger, heavier aircraft, designs that paired the new maneuvering philosophy with the range, the payload, and the powerful radar systems needed to operate across the full scope of the air superiority mission. These aircraft could fight at close range, with the agility the era demanded. They could also engage at distance, with the radar-guided weapons that gave them reach. They could fly further, stay airborne longer, carry more. They were not as light on their feet as their smaller counterparts, but they brought capabilities to the fight that the lightweights, for all their agility, could not match. The pairing was deliberate, high and low, large and small, range and agility, working together to cover the full spectrum of what air combat required. It was an acknowledgement that no single aircraft could optimize everything, and that the honest answer to that limitation was to build a team. The pilots who flew these new machines were, themselves, the product of the reformed training philosophies that Vietnam had demanded. The programs that had been developed to restore and develop close-range combat skills had matured, deepened, become more sophisticated in their understanding of what pilots needed to learn and how best to teach it. Training had become more realistic in the most fundamental sense, more closely modeled on the actual conditions of combat, less filtered through assumptions about what combat would look like. Pilots flew against other pilots in dedicated adversarial training, in aircraft that simulated the performance and tactics of potential opponents. The feedback was immediate and unambiguous. You either won or you did not, and if you did not, there was something to learn from why. The sophistication of the training matched the sophistication of the aircraft. Pilots needed to understand fly-by-wire systems, to understand the behavior of aerodynamically unstable platforms, to understand energy management in aircraft whose performance envelopes were dramatically larger than anything previous generations had trained on. The intellectual demands of flying these machines were substantial, and the training programs reflected that. The pilot who climbed into a frontline fighter of the late 1970s or 1980s was, by any reasonable measure, among the most thoroughly prepared aviators in history. Underlying all of this, the new aircraft, the reformed training, the emphasis on maneuverability, was a concept that had crystallized into doctrine with a clarity it had not previously possessed. Air superiority, the condition in which your forces can operate in the air without prohibitive interference from the enemy, while denying the enemy that same freedom. It was not a new idea. Airmen had understood its importance since the First World War, but it had been elevated, in the strategic thinking of the major air powers, to a position of primacy. The first task, the enabling condition upon which everything else depended. Ground forces could not be effectively supported from the air without it. Naval forces could not operate without it. The entire conduct of modern warfare, as it was now understood, rested on the foundation of air superiority. Building the aircraft to achieve and maintain that condition, designing them from the ground up around the requirements of the close-range maneuvering fight, investing in the training to use them to their full potential, fielding them in numbers and combinations that could meet the threat, was not merely a technical project. It was a strategic commitment. A statement about what air power was for and what it needed to be able to do. The fighters of the 1970s and 1980s were that commitment made physical. They were fast when speed was needed, agile when agility was needed, aware through their senses of what was happening around them, and flown by pilots prepared, more thoroughly than any before them, for the fight those aircraft were built to win. The sky had become something new again. More contested, more demanding, more shaped by technology than it had ever been. And the aircraft rising to meet those demands were, in every sense, equal to them. Chapter 6. Stealth and low observability. Designers began asking a different question. For decades, the central questions of fighter aircraft design had been variations on a familiar theme. How fast could it fly? How high could it climb? How tightly could it turn? How far could it reach? How much could it carry? These were the metrics that defined excellence, the numbers that filled the performance charts and drove the competition between designers and nations. Speed, altitude, thrust, agility. The qualities that made an aircraft formidable were, in the main, qualities that could be measured in straightforward physical terms. But now a different question was being asked, in research facilities and design offices that were, for reasons that would become apparent, kept extremely quiet. Not how fast, not how high, not how agile. whether it could be seen at all. It was a question that required a complete rethinking of what an aircraft was supposed to be, not just in its performance, but in its fundamental relationship with the environment it flew through. And the answers that emerged from that rethinking would produce some of the most unconventional, most consequential, and most quietly revolutionary aircraft that had ever been built. The concern had been building for years, growing in proportion to the improving capability of the radar systems that defended the airspace combat aircraft were being asked to penetrate. Ground-based radar networks had become more sophisticated, more difficult to jam or deceive, more capable of tracking fast-moving aircraft at long range and handing off that tracking data to missile systems with the speed and accuracy to act on it. Airborne radar, carried in interceptors and in dedicated early warning aircraft, extended the coverage further. The picture available to a defended nation's air defense system had become more complete, more reliable, and more lethal than at any previous point in aviation history. Against this backdrop, the conventional approach to survivability, fly faster, fly higher, use electronic countermeasures to confuse the radar, accept some losses as the cost of the mission, was beginning to feel insufficient. The mathematics of modern air defense were becoming unfavorable. Detection ranges were long. Missile engagement envelopes were large. An aircraft that could be detected at 50 miles was an aircraft that had given the defense a great deal of time and space to react. The logic that followed was straightforward, even if the engineering it demanded was anything but. The way to survive in a heavily defended environment was not to outrun the defense, or outmaneuver it or jam it. It was to ensure that the defense never knew you were there. Reduce the radar signature of the aircraft, the strength of the signal it returned to a radar receiver, to the point where detection ranges shrank from 50 miles to 5, or to 1, or to nothing at all. Make the aircraft effectively invisible to the systems hunting it, and the entire calculus of the mission changed. This was the logic of stealth. And the engineers who were asked to make it real faced challenges unlike anything the aviation world had previously encountered. Radar works by transmitting energy, radio waves, in a given direction, and then listening for the echo that returns when those waves strike an object and bounce back toward the receiver. The strength of that echo, what engineers call the radar cross-section, depends on a number of factors: the size of the object, the materials it is made of, and, critically, its shape. The angle at which a surface is presented to incoming radar energy determines how much of that energy is reflected back toward the source and how much is deflected away in other directions. A conventional aircraft, with its curved fuselage and its round engine inlets and its weapons hanging visibly below its wings, is a reasonably good radar reflector. It returns a recognizable echo. It announces itself. The designers of stealth aircraft set out to change that relationship fundamentally. The shape of the aircraft, every surface, every angle, every edge, was conceived not primarily in aerodynamic terms, but in electromagnetic terms. Surfaces were angled so that incoming radar energy would be deflected away from the transmitter rather than returned to it. Edges were aligned in specific orientations that concentrated any remaining reflections into narrow, predictable directions rather than scattering them broadly. The curves and rounds and convenient shapes of conventional aircraft design were replaced by flat panels meeting at precise angles, the result looking, to eyes accustomed to the organic forms of previous generations of aircraft, startlingly angular. Almost geometric. Like something assembled from flat pieces of paper rather than sculpted from metal. The visual strangeness was not incidental. It was the direct consequence of designing for electromagnetic rather than aerodynamic optimality. The shape that minimized radar cross-section was not the shape that minimized drag or maximized lift. It was a different shape entirely, arrived at through a different logic, and it looked different because it was different, fundamentally, categorically different from everything that had come before. Shape alone was not sufficient. The materials from which an aircraft was constructed also played a significant role in determining how much radar energy it absorbed versus reflected. Conventional aircraft materials, aluminum, steel, titanium, were good reflectors. They returned radar energy efficiently. They were, from a stealth perspective, the wrong answer. Radar-absorbing materials worked on a different principle. Rather than deflecting incoming radar energy, they absorbed it, converting it into heat through the electromagnetic properties of the material itself. Developed through research that was itself classified for many years, these materials could be applied to aircraft surfaces as coatings or incorporated into the structural composites from which the airframe was built. In combination with the carefully managed geometry of the aircraft's shape, they reduced the residual reflections that shape alone could not entirely eliminate. The development of effective radar-absorbing materials was not a simple engineering problem. The materials needed to absorb radar energy across a range of frequencies, maintain their properties through the temperature extremes of flight, survive the mechanical stresses of an operational aircraft, and be manufacturable in quantities sufficient to build real aircraft rather than laboratory prototypes. Each of these requirements demanded sustained research, careful testing, and the solution of problems that had never previously needed to be solved. The materials science behind stealth aircraft was, in its own right, a significant technological achievement, one that received far less public attention than the dramatic shapes of the aircraft it enabled, but was no less essential to their capability. Shaping the airframe and selecting the right materials addressed the signature of the aircraft itself. But a conventional aircraft carries its weapons externally, hung beneath the wings and fuselage on pylons, visible and accessible and easy to load and service. Each of those weapons, projecting into the airflow, contributes its own radar return to the total signature. A beautifully optimized low observable airframe studded with external weapons would see much of that optimization undone by the missiles and bombs hanging beneath it. The solution was to bring the weapons inside. Internal weapons bays, enclosed cavities within the fuselage, sealed by doors that remained closed until the moment of weapons release, allowed the stealth aircraft to carry its armament without exposing it to radar scrutiny. The weapons simply did not exist, from a radar perspective, until the bay doors opened. And the bay doors opened only briefly, only at the moment of release, before closing again and restoring the clean, low observable profile. Internal weapons bays added complexity and cost. They limited, to some degree, the variety and quantity of weapons that could be carried. The internal volume of an airframe being finite in ways that external pylons are not. But they were not optional. An aircraft that sacrificed its low observable characteristics to carry its weapons externally was, to a significant degree, defeating its own purpose. The internal bay was not a feature of stealth aircraft. It was a requirement. The shapes that resulted from this design philosophy were unlike anything that had previously flown in operational service. Angular. Facete. In some cases, so unconventional in their geometry that they seemed to challenge the intuition that aircraft should look like aircraft. One design, a dedicated attack aircraft, the first operational stealth aircraft, was so angular, so composed of flat panels meeting at sharp angles, that pilots who first encountered it sometimes struggled to reconcile its appearance with their understanding of what a flying machine should look like. Its wings swept back at extreme angles. Its fuselage was a collection of flat surfaces carefully arranged to deflect radar energy in directions away from any receiver. It had no curves to speak of. It looked, to some eyes, like a folded piece of paper that had somehow learned to fly. Another design took a different approach, using a smooth, blended shape where the entire aircraft was conceived as a single continuous surface, a flying wing, with no distinct fuselage, no tail surfaces, the crew and the weapons and the engines all enclosed within an airframe that was itself a wing of extraordinary span. This design was not angular but organic, its smooth curves serving the same electromagnetic purpose as the sharp angles of its predecessor through a different geometric logic. It was, in its own way, as striking an object as the angular design, vast, quiet, shaped like something from the imagination. Both were flying. Both were operational. Both were, to radar systems searching the sky for them, very close to invisible. Invisibility, as a combat capability, changed the nature of the missions that could be planned. An aircraft that could penetrate defended airspace without being detected did not need to fight its way through the defense. It did not need fighter escorts to suppress interceptors that never knew it was coming. It did not need the elaborate packages of jamming aircraft and missile suppression flights and carefully timed corridors that conventional strike packages required. It could simply go where it needed to go, at the time that best served the mission, and arrive unannounced. This enabled a precision and a surprise that had not previously been achievable against heavily defended targets. The first moments of a conflict, the critical opening strikes against air defense networks, command facilities, and high-value targets, could be carried out before the defense had any meaningful chance to react. Targets that would have required large, complex strike packages and accepted significant losses could now be addressed by small numbers of aircraft operating in the early hours of a campaign, with a precision that concentrated effect and minimized collateral consequence. The missions changed in character. They became quieter, more deliberate, more dependent on planning and precision and the careful management of timing than on the brute force application of numbers and speed. Stealth did not make combat simple. The planning required to exploit low observable capabilities effectively was enormously complex. But it fundamentally altered the relationship between the attacking force and the defending one, and that alteration was, from the attacker's perspective, enormously favorable. The detection ranges that radar systems could achieve against conventional aircraft and against stealth aircraft were not published and are not fully known outside the classified world. But the operational evidence, the campaigns in which stealth aircraft participated, the way those campaigns were planned and executed, the results they achieved, tells a clear enough story. An aircraft that required the defense to detect it at 50 miles in order to mount an effective response, and that instead revealed itself at 5, had not merely reduced a number. It had, in practical terms, removed the defense from the equation entirely. The window in which the defense could act had collapsed to a point where acting effectively was, in most scenarios, impossible. This was the capability that stealth provided. Not invulnerability. No aircraft is invulnerable, and stealth aircraft operated within real constraints and accepted real risks. But a profound, operationally decisive reduction in the ability of a defended environment to find, track, and engage the aircraft penetrating it. Against the right targets, in the right conditions, a small number of stealth aircraft could accomplish what large numbers of conventional aircraft could not. Not because they were faster or more powerful or more maneuverable, but because they could not be seen. The impact of stealth on fighter and attack aircraft design proved to be permanent. Once the capability existed, and once its operational value had been demonstrated, it could not be set aside. Future aircraft, not just dedicated stealth designs, but the mainstream of combat aircraft development, had to grapple with the low observable question. Some degree of attention to radar signature became a standard consideration in new designs, even for aircraft that were not conceived as stealth platforms in the dedicated sense. The shapes of aircraft changed. The materials used in their construction changed. The way weapons were carried, the way inlets were designed, the way every surface was considered in the context of its electromagnetic as well as its aerodynamic properties. All of it was different because stealth had arrived and had demonstrated what was possible. The question that designers had begun asking, not how fast, but whether it could be seen, had reshaped the entire field. Speed remained important. Agility remained important. Range and payload and sensor capability all remained important. But to all of those existing criteria, stealth had added one more, quiet and transformative. Visibility. The question of whether the aircraft announced itself to the world it flew through, or passed through it in silence, unseen, arriving and departing without the sky recording its presence. The answer, for the best of this new generation of aircraft, was silence. Chapter 7. The Digital Fighter Era. Aircraft became more than machines. It happened gradually, and then all at once, the way most profound changes happen, accumulating quietly beneath the surface until the moment when the new reality is simply undeniable. The fighters of previous generations had been remarkable achievements of engineering and aerodynamics, shaped by speed and agility and stealth and the accumulated lessons of decades of combat. They were, in every meaningful sense, extraordinary machines. But they were, fundamentally, machines, self-contained, flying independently through the sky, their awareness bounded by what their own sensors could detect and what their pilots could perceive and process in the demanding environment of the cockpit. The fighters of the digital era became something different. They became nodes, points in a network that extended far beyond the aircraft itself, connecting to satellites and ground stations and other aircraft and ships and, in time, to almost any platform that carried the right equipment and the right software. The aircraft still flew. The pilot still flew it. But the information flowing through that aircraft, the awareness it carried of the world around it, the decisions it could support and the actions it could enable, all of it had been transformed by the digital revolution that was simultaneously reshaping every other domain of human activity. They became part of a network. And the network, it turned out, changed everything. Information, in aerial combat, had always been the decisive resource. The pilot who knew where his enemy was, and was not himself known, held an advantage that often proved decisive regardless of other factors. Speed helped. Agility helped. Weapons capability helped. But awareness, the ability to build and maintain an accurate picture of what was happening in the sky around you, was the foundation upon which all other advantages rested. The challenge had always been that building that picture was hard. The sensors available to a single aircraft, its radar, its infrared systems, its electronic warfare receivers, each provided a partial view. Each had range limitations, blind spots, conditions under which they performed less well. And each produced information in its own format, through its own display, requiring the pilot to synthesize multiple partial pictures into a single mental model of the situation while simultaneously flying the aircraft, managing its systems, and making decisions under pressure. The human mind is capable of remarkable things under pressure. But it has limits. And as aircraft became more capable, as the speed and complexity of the combat environment increased, those limits were being approached. Pilots were managing more information than any previous generation had been asked to manage. The cognitive load of modern aerial combat had become one of the most demanding challenges in military aviation. Sensor fusion was the answer that the digital era provided. Rather than presenting the pilot with separate streams of information from separate sensors, and asking the human mind to integrate them, sensor fusion allowed the aircraft's computers to do that integration automatically. Data from the radar, from the infrared search and track system, from the electronic warfare suite, from the data link connecting the aircraft to other platforms, all of it was processed, correlated, and presented to the pilot as a single, coherent picture. Not raw data requiring interpretation, but synthesized awareness requiring decision. The difference was profound. The pilot was no longer a data processor struggling to keep up with incoming information. He was a decision maker, presented with the situation as clearly and completely as the technology could construct it, free to think about what to do rather than laboring to understand what was happening. The cockpit that surrounded the pilot of a digital-era fighter was, visually, almost unrecognizable compared to the instrument panels of earlier generations. Where previous cockpits had been populated with dozens of individual dials and gauges, each measuring one thing, each requiring the pilot's attention to be read and interpreted, the modern cockpit was organized around large, high-resolution displays. Glass screens, configurable in real time, showing the pilot whatever information was most relevant to the current phase of flight and the current demands of the mission. The tactical display showed the world around the aircraft, the positions of friendly and enemy platforms, the locations of threats, the geometry of the engagement, as a clear, intuitive picture that updated continuously as the situation evolved. Navigation, weapons management, system status, communication. All of it was integrated into the same digital environment, accessible from the same displays, managed through the same interface. The philosophy behind this design was the philosophy of the human factors engineer applied to the most demanding operational environment imaginable. Reduce the work required to find information. Reduce the number of separate displays the pilot's eyes needed to travel between. Present the most important things most prominently, and allow less critical information to recede until it was needed. The cockpit was no longer a collection of instruments that happened to be installed in the same small space. It was a designed information environment, built around the cognitive needs of the person at its center. Pilots who transitioned from older aircraft to digital cockpits often described the experience as a revelation. Not because the new aircraft were necessarily easier to fly in the physical sense, but because the mental effort required to stay aware of the situation had decreased dramatically. Energy that had previously been spent managing information could now be spent using it. Even the most sophisticated cockpit display, however, requires the pilot to look at it. And looking at a display inside the cockpit means, for that moment, not looking outside. In the close-range, high-speed environment of aerial combat, moments matter. The fraction of a second spent looking down at a screen is a fraction of a second not spent watching the sky. The helmet-mounted display addressed this limitation in the most direct way possible. It brought the display to wherever the pilot was looking. A system that projected targeting information, aircraft status, and situational awareness data directly onto the visor of the pilot's helmet meant that the pilot did not need to look away from the outside world to access critical information. The data was there, overlaid on reality, visible regardless of where the pilot's head was pointed. The implications for weapons employment were significant. Earlier aircraft required the pilot to point the aircraft's nose toward a target in order to bring the weapon system to bear. The weapons, and the sensors that guided them, were fixed to the aircraft's axis. A helmet-mounted sight, connected to a missile that could be launched off-axis, allowed the pilot to simply look at a target. Look, and the weapon system followed. Look, and the missile was already pointed where it needed to go. This capability, the ability to engage targets that were not directly in front of the aircraft, targets off to the side, behind, above, in geometries that previous generations of weapons could not have addressed, changed the geometry of close-range combat fundamentally. The requirement to maneuver into a specific firing position before engaging was relaxed. The pilot who could see a threat could address it, in a much wider range of situations, from a much wider range of positions, than had previously been possible. Awareness and lethality had been connected to each other more directly than ever before. The network that transformed the digital era fighter was not contained within the aircraft itself. It extended outward, through data link systems, to every other platform that was part of the same operational picture. Other aircraft. Airborne early warning platforms, carrying powerful radars that could see further and more completely than any single fighter. Ground stations with access to intelligence feeds and strategic information. Naval vessels with their own sensors and weapons. Satellites providing navigation, communication, and in some cases direct intelligence. An aircraft flying within this network was not limited to what its own sensors could detect. It could receive the radar picture from an airborne warning aircraft 100 miles away, seeing targets that its own radar could not reach. It could share its own sensor data with other aircraft in the formation, contributing to a collective picture that was richer and more complete than any single platform could construct alone. It could receive targeting data from a ground station, engage a target it had never directly detected, and return to base with the mission complete and the network no longer showing the threat. The individual aircraft had become, in a very real sense, a participant in a collective intelligence. The pilot's awareness was no longer bounded by the range of his own systems. His awareness was bounded by the range of the network, which was, in operational terms, vastly larger. This had consequences for tactics, for doctrine, for the way missions were planned and executed. It also had consequences for the adversary, who now faced not merely individual aircraft but a coordinated, information-sharing system that could concentrate effect from multiple directions simultaneously, that was far harder to deceive because the deception that fooled one node did not fool the network, and that could adapt to changing situations with a speed and coherence that individual, isolated aircraft could not match. Beneath all of the sensors and displays and data links, making all of it work, was software. Lines of code, millions upon millions of them, running continuously on processors embedded throughout the aircraft, managing systems that would have been unmanageable by any other means. The fly-by-wire computers of the previous generation had been an early indication of what software could do for an aircraft. The digital-era fighter extended that principle across every system in the airframe. The radar's signal processing, the sensor fusion algorithms integrating multiple data sources, the mission planning systems, the weapons management software determining which weapon was best suited for which target, the electronic warfare systems analyzing threats and generating responses, the communications management routing information across the network. All of it was software. All of it was, in a meaningful sense, as important to the capability of the aircraft as the engine or the wing. And software, unlike metal, could be updated. A discovery made in operational use, a new threat, a new tactic, a new requirement, could be addressed through a software update rather than a physical modification. The capability of the aircraft was not fixed at the moment it left the factory. It could evolve, be refined, be extended, as long as the underlying hardware could support the new code. The aircraft was, in this sense, a platform, a foundation on which capability could be built and rebuilt over time. This was a different relationship between an aircraft and its development than anything that had come before. The design was never truly finished. It was always in progress, always being improved, the software reflecting an ongoing conversation between operational experience and engineering capability. The multi-role capability that Vietnam had argued for, and that subsequent decades had developed, reached its fullest expression in the digital era. The modern frontline fighter was not a specialized machine optimized for one mission and tolerant of others. It was a genuine all-rounder, capable of air-to-air combat against the most capable opponents, of precision strike against defended ground targets, of electronic warfare, of reconnaissance, of close air support, performing all of these missions with a level of effectiveness that earlier generations of specialized aircraft would have found remarkable. The technology that made this possible was the same digital technology that defined the era. A single airframe, carrying the right sensors and the right software and the right weapons, could be configured for whatever the mission required. The radar that searched for airborne targets could be directed downward to map the ground. The weapons bay that carried air-to-air missiles could equally carry precision-guided bombs. The data link that connected the aircraft to the air defense network could equally connect it to ground forces calling for support. Flexibility had become, in the digital era, a form of power in itself. An adversary who could predict exactly what a platform would do, and exactly how to counter it, faced a simpler problem than one who faced a system that could adapt, that could be something different tomorrow than it was today, that could perform missions it had not been performing yesterday, that could surprise. The precision with which weapons could be delivered had also undergone a transformation that, while not always as visible as the dramatic shape of a stealth aircraft or the glowing screens of a digital cockpit, had consequences every bit as significant. Guided weapons, precision munitions that could be directed to their targets with accuracy measured in meters rather than hundreds of meters, had been developing since the Vietnam era. In the digital age, they had matured to the point where a miss, for a well-equipped aircraft with a properly functioning weapons system, was an exceptional event rather than a routine one. This precision changed the math of air power. Where earlier campaigns had required dozens or hundreds of unguided weapons to achieve reliable destruction of a single target, a single precision-guided munition could accomplish the same result. Fewer aircraft were needed for the same effect. Fewer sorties meant less exposure to threat, and the ability to place a weapon exactly where it was intended reduced, enormously, the unintended consequences that had accompanied less precise methods. Precision was not merely a technical achievement. It was a strategic one, changing what was possible, what was acceptable, and what was expected from the application of air power in ways that reshaped doctrine and policy as thoroughly as any new aircraft type had ever done. At the center of all of this technology, the networks and the sensors and the software and the displays and the precision weapons, remained the pilot. Changed in role, elevated in some ways and constrained in others, but irreplaceable. The pilot of a digital-era fighter was, in the most demanding moments, a real-time manager of extraordinary complexity. Systems required monitoring and input. The network required contribution. The pilot was not merely a receiver of information but a participant in it, feeding his own aircraft's sensor data back into the collective picture, making decisions that affected not just his own aircraft but the operation as a whole. Weapons required selection and employment. The tactical situation required continuous assessment. The cognitive demands were different from those of previous generations. Less about raw physical skill, more about the management of information and the quality of decision-making under pressure. But the underlying qualities that had always defined excellence in the cockpit had not disappeared. Awareness, judgment, the ability to act decisively when the moment required it and to hold back when patience served better. The temperament to function clearly when the situation was confused and the stakes were absolute. Technology had changed almost everything about how a fighter aircraft performed. It had not changed what a pilot needed to be. The sky was a network now. Information flowed through it like weather, invisible, omnipresent, shaping everything. And the aircraft that moved through that sky carried, in their software and their sensors and their data links, a kind of awareness that their predecessors could not have imagined. They were machines still. They needed pilots still. But they were part of something larger than themselves now, a connected, sensing, thinking system that extended from the cockpit to the satellite and back again. The fighter had become a node in a vast and invisible architecture of information. And from that architecture, with all its complexity and all its capability, the future of aerial combat was already beginning to take shape. Chapter 8. The future of fighter jets. The story is still unfolding. It has always been unfolding, of course. Every chapter in the history of the fighter aircraft has been written in real time, by people who could not fully see what came next, engineers working at the edge of what was understood, pilots flying aircraft that had never been flown before, commanders making decisions with incomplete information about how the technology would behave when it met the unforgiving reality of operational use. The story has never been tidy. It has never followed a straight line from one point to the next. It has doubled back, surprised its participants, demanded revisions to conclusions that seemed settled. But there is something particular about the present moment. The threads that are gathering now, the unmanned systems, the artificial intelligence, the directed energy, the hypersonic research, the gradual, careful expansion of autonomy, represent a convergence that feels different in character from the incremental improvements that have defined most of aviation history. Not merely faster or stealthier or more connected than what came before. Something more fundamental. A renegotiation of the basic terms on which aerial warfare has been conducted since the first armed aircraft climbed into a contested sky. New ideas are forming quietly. The next generation is already on the horizon. And the horizon, for those who study it carefully, looks unlike anything that has preceded it. The unmanned aircraft is not a new idea. Remotely piloted vehicles have existed in various forms for decades, performing reconnaissance missions, providing surveillance, and in more recent years delivering weapons with a precision that has made them operationally significant in conflicts around the world. They have demonstrated, beyond any reasonable argument, that an aircraft without a human being physically present in the cockpit can be an effective military tool. What is new is the conversation about how unmanned systems relate to crewed fighters, not as separate categories of capability operating in their own domains, but as partners, teammates. The concept that is emerging, and that is being actively developed and tested in programs around the world, is one in which a crewed fighter operates alongside one or more unmanned wingmen, aircraft that fly in coordination with the human pilot, extending the reach of the formation, absorbing risk, performing tasks that benefit from the presence of an aircraft in a specific place without requiring a human being to be in that place. The unmanned wingman can go first into a heavily defended environment, probing the defenses, absorbing attention, presenting the adversary with more targets than can be engaged simultaneously. It can carry additional weapons, extending the magazine depth of the formation. It can carry sensors, pushing the awareness of the crewed aircraft further out than its own systems can reach. It can, in certain scenarios, take actions that a human pilot physically present in the cockpit could not safely take, accepting acceleration loads, for example, that would incapacitate a person, or flying profiles that require more endurance than biology permits. The pairing is not about replacing the human pilot. It is about amplifying what the human pilot can do, giving one person the effective reach and presence of a formation that would previously have required multiple crewed aircraft and multiple pilots to field. The human remains at the center, making the decisions that require judgment and awareness and the kind of contextual understanding that machines do not yet possess. The unmanned systems extend the consequences of those decisions across a larger volume of sky. Extending those decisions, and supporting the human mind in making them better and faster, is the role that artificial intelligence is beginning to play in the cockpit and in the broader system of which the cockpit is a part. The digital era had already moved the pilot from data processor to decision maker, using sensor fusion and integrated displays to present a clearer picture with less cognitive effort. Artificial intelligence represents the next step in that progression. Systems that do not merely present information but analyze it, that do not merely display options but evaluate them, that can process the full complexity of a rapidly evolving tactical situation and offer the pilot recommendations that would take an unaided human mind longer to develop. In the time available during aerial combat, seconds, fractions of seconds, the quality of a decision can determine everything. An AI system that can model the current situation, project its likely evolution, identify the highest probability threats and the highest value opportunities, and present that analysis to the pilot in a form that can be acted upon immediately is not replacing the pilot's judgment. It is extending it. It is giving the human mind at the center of the system access to a depth of analysis that no human, however skilled and experienced, could produce alone in the time available. The AI systems under development for combat aviation are not the fictional intelligences of science fiction, omniscient, independent, pursuing their own agendas. They are tools, sophisticated and capable tools, designed to do specific things well in specific environments. What they do well is process large amounts of information very quickly and identify patterns within it. What they support is the human decision-maker who acts on what they find. The partnership between human judgment and machine processing that has been developing throughout the digital era is becoming, with artificial intelligence, more equal and more capable than at any previous point. Speed has been a defining theme throughout the entire history of the fighter aircraft. From the first jets that left propellers behind, to the afterburner-equipped supersonic aircraft of the 1960s, to the high-performance agile fighters of the 1970s and beyond, each generation has pushed further against the limits of how fast an aircraft could go. And now, at the frontier of current research, a new threshold is being approached, one that makes supersonic flight seem, in relative terms, almost modest. Hypersonic. The term refers to speeds above Mach 5, 5 times the speed of sound. At those velocities, the physical environment experienced by an aircraft changes in ways that make even supersonic flight look straightforward by comparison. The heat generated by air compression at hypersonic speeds is extreme. Surfaces reach temperatures that would destroy conventional materials in seconds. The aerodynamic forces are enormous and behave in ways that require entirely new approaches to design and stability. The time available for guidance and control decisions is compressed to the point where autonomous systems, operating faster than any human can direct, become not merely useful but necessary. Hypersonic research is ongoing, pushing forward in laboratories and test ranges, working through the formidable engineering challenges that stand between current capability and operational hypersonic weapons and vehicles. Progress is real, even when it is slow. Materials that can survive the thermal environment of hypersonic flight are being developed. Propulsion systems that can sustain those speeds, the scramjet engines that breathe air rather than carrying oxidizer, enabling speeds that rocket propulsion alone cannot efficiently sustain, are being refined. The trajectory from research to operational capability is measured in years and decades rather than months, but the direction is clear. An operational hypersonic weapon changes the defensive calculus in a way that even stealth did not fully achieve. A stealthy aircraft can be invisible, but once detected, it moves at speeds a defense can work with. A hypersonic weapon, closing at Mach 10 or beyond, compresses the reaction time available to any defense to the point where the geometry of interception becomes extraordinarily difficult. The combination of low observability and hypersonic speed, a target that cannot be easily seen and, once detected, cannot be easily stopped, represents a challenge to defensive systems that current technology has no complete answer to. The aircraft that will carry these capabilities, that will fly alongside unmanned wingmen and draw on artificial intelligence and eventually deliver hypersonic weapons, will be built from materials that do not yet exist in production quantities, incorporating properties that current manufacturing cannot yet achieve at operational scale. The development of new materials has been a constant thread through the history of aviation. Each generation of aircraft has demanded materials that were lighter, stronger, more resistant to heat, more capable of being formed into the precise shapes that aerodynamic performance required. The progress has been remarkable, from the wood and fabric of the earliest aircraft to the aluminum alloys of the jet age to the composites and special metals of the stealth era. Each step enabled capabilities that the previous materials could not have supported. The materials being developed for the next generation continue that progression. Composites that are stronger and lighter than those currently in use. Coatings that can withstand the thermal environment of hypersonic flight. Structural materials that can be manufactured with greater precision and consistency, reducing weight while maintaining the strength that safety demands. Materials that are not merely passive structural elements but active participants in the aircraft's function, absorbing radar energy more effectively, dissipating heat more efficiently, contributing to the low observable and thermal management requirements that stealth and high-speed flight impose. Some of these materials exist in the laboratory. Some exist in limited production. Some are still more concept than substance, waiting for manufacturing processes to catch up with scientific understanding. The path from laboratory demonstration to operational aircraft is long and difficult, but the direction of travel is well established. The complexity of modern combat aircraft, the systems, the software, the sensors, the weapons, has always created a tension with the desire for longevity. An aircraft designed today to a specific set of requirements will be flying 20 or 30 years from now, in an environment that will have changed in ways that no one can fully anticipate. The threat will be different. The technology available to address it will be different. The missions the aircraft is asked to perform may be substantially different from those that drove its original design. The modular approach to aircraft systems, designing components to be replaced and upgraded over time rather than fixed permanently at the point of manufacture, represents an attempt to manage this tension honestly. If the radar that equips an aircraft today can be removed and replaced with a more capable system when one becomes available, the aircraft does not become obsolete when radar technology advances. If the software that manages the aircraft's sensors and weapons can be updated continuously, the aircraft can incorporate new capabilities as they mature without requiring physical modification. This philosophy extends the useful life of expensive platforms and reduces the pace at which they become obsolete. It also creates a different relationship between aircraft manufacturers and the military organizations that operate their products, a more continuous relationship, a longer conversation, an ongoing collaboration that persists through the decades of an aircraft's service life rather than ending at delivery. The aircraft of the future is not a finished product. It is a platform, in the fullest sense, a foundation on which capability can be continuously built, adapted, and rebuilt as the world it flies in continues to change. The contest between aircraft and the electronic environment they operate in has been continuous since radar first reached into the sky to find them. It has never paused, never settled into a stable equilibrium where one side had achieved a decisive and permanent advantage. Each development in detection capability has been answered by a development in concealment or deception. Each improvement in electronic warfare has been met by improvements in the systems it seeks to counter. That contest continues, and it continues to accelerate. The electronic warfare systems of the coming generation will operate across wider ranges of the electromagnetic spectrum, with greater sophistication, against threats that are themselves more capable than those they replace. They will be more deeply integrated with the aircraft's other systems, the radar, the data link, the weapons, using the same information for multiple purposes simultaneously. They will increasingly rely on software and artificial intelligence to recognize threats and generate responses faster than human operators can direct. The electromagnetic environment in which future aircraft will operate is, if anything, more complex and more contested than the physical one. The ability to navigate that environment, to find and use the spaces within it, to deny those spaces to an adversary, to understand what the electronic world is revealing about the situation around the aircraft, will be as important a capability as any aerodynamic quality the airframe possesses. Among the most consequential and quietly transformative technologies under development for future combat aircraft are directed energy weapons, systems that deliver their destructive or disruptive effect not through a projectile or an explosive, but through energy itself. Lasers, high-powered microwave systems, beams of electromagnetic energy that travel at the speed of light, that require no ammunition in the conventional sense, and that can be applied with a precision that mechanical weapons cannot match. The appeal is significant. A weapon that travels at the speed of light does not require the lead calculation that a projectile does. It goes where it is pointed, instantaneously. A weapon that draws its power from the aircraft's engine requires no magazine, no finite stock of rounds or missiles to be exhausted. As long as the engine runs, the weapon can fire. And a weapon that can be tuned in its effect, from the gentle disruption of an electronic system to the decisive destruction of a structural component, offers options that explosive weapons do not. The challenges are equally significant. Generating the power levels required for effective directed energy weapons demands energy sources that current aircraft cannot easily provide. Atmospheric effects, humidity, dust, turbulence, degrade the beam over distance in ways that limit effective range. The thermal management of a high-powered laser, which generates substantial heat in the process of generating its beam, adds complexity and weight. These are solvable problems, and progress is being made. But they are genuinely hard problems, and the timeline from laboratory capability to operational deployment remains uncertain. What is certain is that directed energy will change the nature of aerial combat when it arrives, adding a category of weapon with characteristics unlike anything that has come before, and demanding that both tactics and countermeasures evolve to address it. Throughout this entire story, from the first straight-wing jets that appeared over Europe in the closing years of the Second World War to the networked, AI-assisted, low-observable platforms of the present, the pilot has been at the center. Changed enormously in role, equipped with capabilities that would have been literally unimaginable to earlier generations, asked to manage systems of extraordinary complexity in environments of extraordinary demand. But present, essential, irreplaceable. The question of whether that will remain true is one of the most genuinely uncertain in the future of aviation. Autonomy is increasing. Unmanned systems are demonstrating capabilities that expand with each generation of development. The tasks that require a human being physically present in the cockpit are, slowly and unevenly, being examined for whether they truly require that presence or whether they can be performed as well or better by systems that do not need to sustain a human life in the process. The answer, for the foreseeable future, is that the pilot remains. Not unchanged, the role will continue to evolve, the balance between human decision-making and machine capability will continue to shift, and the specific skills that matter most in the cockpit will continue to be redefined by the technology surrounding them. But present, the qualities that have always distinguished the exceptional aviator, judgment, awareness, the ability to act wisely in conditions of uncertainty and pressure, are not qualities that can yet be replicated in software. They may never be, in the full sense. The human mind, shaped by millions of years of evolution to navigate a complex and unpredictable world, brings something to the cockpit that the machines surrounding it, for all their extraordinary capability, do not yet possess. The pilot of the future will fly differently from the pilots of the past. The aircraft will be different, the information environment will be different, the weapons and the tactics and the doctrine will be different. But the essential act, a human being, in a flying machine, making decisions in the sky, will persist. Changed in almost every particular. Continuous in its fundamental nature. The fighter aircraft began as a propeller-driven machine climbing into the skies of a world war, carrying a pilot in an open cockpit, armed with guns, moving at speeds that would seem almost leisurely by the standards of everything that followed. It became a jet. It went supersonic. It learned to dogfight at speeds that compressed time into fractions of seconds. It became stealthy, invisible, passing through defended airspace like a rumor. It became networked, aware of a world beyond its own sensors, part of a system that extended from its cockpit to a satellite and back again. And now it is becoming something else again, something that is not yet fully defined, that exists partly in laboratories and partly in classified programs and partly in the minds of engineers and pilots and planners who are working, at this moment, to shape what comes next. Unmanned wingmen flying alongside human pilots. Artificial intelligence deepening the awareness available in the cockpit. Directed energy weapons changing the nature of what it means to engage a threat. Hypersonic speeds redrawing the geometry of what is possible and what can be defended against. The story is still unfolding. It has always been unfolding. And the next chapter, like every chapter before it, will be written in the sky by the people and the machines that rise into it, carrying with them everything that has been learned and built and fought for across more than 80 years of the jet age. The horizon is there. It always is. And beyond it, as always, something new is coming. And so it ends, or rather, pauses. Because a story like this one does not truly end. It has no final chapter in the conventional sense, no closing scene where the last aircraft lands and the hangar doors close and the lights go out. The engineers are still working. The pilots are still flying. The programs that will produce the next generation of aircraft are already underway, in facilities and research centers around the world, drawing on everything that has been learned and pushing toward everything that has not yet been achieved. The story of the fighter jet is a story that is still being written. Tonight, we have read what has been written so far. Think for a moment about how much ground we have covered. We began with straight-winged jets appearing over wartime Europe. Cautious, imperfect, revolutionary machines that replaced the propeller with something new and in doing so opened a door that could never be closed again. We watched those early aircraft evolve, over the Korean War years, into swept-wing fighters meeting each other in combat at speeds that compressed the geometry of aerial engagement into something entirely unfamiliar. We crossed the sound barrier, quietly, almost matter-of-factly, as though breaking one of the most famous physical thresholds in aviation history was simply the next logical step. Which, by then, it was. We followed the painful education of Vietnam, where combat refused to conform to doctrine and the aviation world responded with the particular honesty of people who understand that experience, however uncomfortable, is more valuable than assumption. We watched designers build agility back into aircraft that had been optimized almost entirely for speed, and saw fly-by-wire computers make possible the deliberately unstable aircraft that no human hand alone could have flown. We passed through the quiet revolution of stealth, aircraft shaped not for the sky but for the electromagnetic spectrum, designed to be invisible rather than fast, arriving at their targets before the defense knew they were coming. And we arrived in the digital present, where aircraft are nodes in a network, where sensors fuse their outputs into a single coherent picture, where artificial intelligence begins to extend the reach of human judgment, and where the horizon ahead holds directed energy and hypersonic flight and the gradual, careful expansion of autonomy into domains that have always belonged to the human pilot. 8 decades. An unbroken thread of curiosity and ingenuity and hard-won experience. And we have followed it, tonight, from one end to the other. There is something worth carrying with you from this story. if you choose to carry anything at all. It is this: every capability that now seems routine was, at some point, impossible. The jet engine was a speculation before it was an experiment, and an experiment before it was a production aircraft, and a production aircraft before it was the obvious and only way to power a modern fighter. The sound barrier was a wall before it was a door. Stealth was a classified research program before it was an operational aircraft, and an operational aircraft before it was a permanent feature of how combat aviation thinks about itself. The digital cockpit, the data link, the sensor fusion, the helmet-mounted sight, all of it was, at some point, a drawing on a piece of paper in someone's office, or an equation on a whiteboard, or a conversation between engineers who were not entirely sure it was possible but were going to find out. The impossible has a way of becoming the standard, in aviation, if you give it enough time and enough people who refuse to accept that the current answer is the final one. That is not a small thing to know. The hours have passed gently, as they were meant to. The voice has carried you through decades of sky and speed and technology and human ingenuity, and now it is drawing quiet. The chapters are complete. The aircraft are, for the moment, at rest. If you are still awake, we hope the journey has been a pleasant one, that there were ideas along the way that caught your attention and held it for a while, details that seemed worth noticing, moments where the sheer strangeness of what human beings have built in the sky struck you with something like quiet wonder. And if you drifted somewhere along the way, if the voice became part of the background of a dream, if the story of jets and pilots and swept wings and stealth dissolved into whatever your sleeping mind made of it, then that is perhaps the best possible outcome. You went somewhere comfortable, and the sky went with you. Rest well. The aircraft are still up there, somewhere above the clouds, moving through the dark with a quiet and continuous force. And tomorrow, as always, the engineers will be back at their desks. The pilots will be back in their cockpits. The story will keep going. It always does. Good night.